So as you can see, the relay tester is still running. You might notice a little bit of a difference in the look of the unit, and that's because yesterday it vibrated off my desk and crashed to the floor, and so I had to repair it, and while I was repairing it I straightened it out a little bit. But we've been testing these relay modules, and right now I have over 125,000 cycles on these relays, and they still are working perfectly fine. You can see I just started a count a little while ago. I am up to 11,120 cycles on each of the relays. So if you count all 4 of the relays, we are up to over 500,000 relay contacts without any problems that we can detect. So these are probably a really good solution. However, I mentioned in the first video that we wanted to test a solid state relay, and we have a solid state relay in. So my plan for tonight is to swap out this 8-channel relay board with the 4-channel mechanical relay board and test it out and see if this functions. As I said, the mechanical relays are a perfectly fine solution, but if we can get away with a non-mechanical solution, we would prefer to have that. I have my doubts actually about these modules working because they don't really specify whether they will handle an inductive load or not. And so we'll hook it up and see. If they don't, we'll go with the relays. If they do, we'll go with the solid state. Okay, as you can see, I now have the new solid state module hooked up. At least I have 4 ports of it hooked up. Connected up to the relay. This is the first connection. So I will plug my connector in. So I'm getting a lot of buzzing that I wouldn't expect. Okay, before I start my test running, I want to talk a little bit about what happened. It turns out that this relay module is configured differently from the old relay module. This relay module, although it doesn't say it on here anywhere, is activated with a low going pulse and deactivated when that line goes back high. This relay, and it's written right on the side here, says high level trigger. Hard to see underneath all the wires. But the reason I was getting all the buzzing is because the solenoids were activating for about 120 milliseconds and then turning off for about 25 milliseconds and then repeating that. So the solenoids were staying on almost all the time, and that was causing the buzzing. It was also causing the solenoids to get very hot. So what I'm going to do now is I'm going to plug in these relays and I'm going to start up a test, and I'll come back when I got the test running, and then I'm going to let that test run for about 30,000 cycles. So be back in a moment. Okay, as you can see, the test is running nice and clean. The relays, solenoids are all activating very smoothly. The lights are pulsing on now instead of being on continuously like they were earlier. And the test is running away, and right now I'm up at about 190 or so, 180. So we will let this test run until we have a few thousand cycles, and then we will stop. So you can see that we've gotten up to about 7,000 cycles. I plan to do at least twice that many or 3 times that many. But for now, I want to talk a little bit about what we're going to do next. Okay, so let's start off by talking about what our plans are for the next phase of this operation. Obviously, we're going to need to wire up a microprocessor, several relay boards, and a whole bunch of switches to control this pinball machine using this microprocessor. Our plan is to design a custom board that will help us accomplish all of this. And what you're looking at right now is a KiCad. I normally pronounce it KiCad, but they pronounce it KiCad. I will probably pronounce it both ways while I'm doing this recording. Sorry about that. But a KiCad schematic board layout of the board we plan to build. It's a little hard to see in this view, so I'm going to show you the 3D model view that KiCad can produce, and with this I can move and pan around and show you the details of the board. So in the middle of the board is the STM32 microprocessor board that is the brain of this entire operation. Now, this board does not have enough ports on it to do all of the work that we need to do. So also on this board are 6 2 8-port expanders. They're MCP 23017s. So there's one here, one on each end, and then there's 2 on each side. And that gives us adequate ports to do everything we need to do. But because the STM32 also has extra ports that we might be able to use, I've brought those ports out into pin headers right in this area, and then down in this area here. Now, the way this board is set up, the port expander on this end and this end are used to create 4 connectors that will plug directly into the relay boards, eliminating the need for wiring between this board and the relay board. Now, when this board was originally designed, it was designed for the pinout of the mechanical relay boards. The solid-state relay boards are slightly different, so I am going to modify this board so that this connector will actually be able to accommodate either type of relay board. It's just going to require me to add another power pin to the end of the connector. So anyway, that's how the relays get attached. And if you need additional relays, this port down here is configured as either an 8-port or a 4-port relay board interface, so you can have another relay board down here. Then these other 4 expanders are used to provide the inputs for all of the switches. And there are a total of 64 inputs here, and then if we need any more, we can use the additional inputs over here and over here. Now, because of the way the STM32 is configured, these pins are 3.3 volt only pins. They are not usable with a 5 volt input. And these pins, while they can be used as digital input pins, are also the analog input pins, so we could attach something like a potentiometer to adjust lamp brightness or anything else that we might want an analog input for. But they could be used for digital pins also if at some point we needed more of those. Now, to give more of an overview of what this might look like, I did a little SketchUp layout that looks like this. So this shows 4 8-port relay boards and 1 4-port relay board connected to this. And so this is what would mount in the back box and would drive all of the electronics. There's no dimensions on this board, but it's about 8 inches across and a little bit longer than a foot long in this particular configuration. It'll be a little bit smaller, I think, with the solid state relays because they're actually smaller. Now, another thing to look at on the design of this board is that there are 6 ground wire terminals here to connect ground wires from different points on the board, 6 power output connectors here to provide 5 volts to anything that might need 5 volts on the board. And it also will provide the 5 volt input for this board. So the power supply will provide input 5 volts and ground into here, and then can be redistributed out to other things that might need it. And then the one last connector is this connector right here, and it's where the LED string will connect that will drive all of the lights that are on the pinball machine. So that's it. That's our next step. Now, you might ask, well, how are we going to have these boards manufactured? There's lots of places to have boards manufactured. I use JLC PCB. I've had about 6 boards manufactured by them. I've used a couple other companies to manufacture little proto-boards. This place is by far the cheapest I've found. You can get a 100 by 100 millimeter board, 2-layer, for just $2. And if you get the inexpensive China landline shipping method, it'll get to you in about 3 weeks, which isn't bad. If you opt for a more expensive shipping method, which will cost you $15 or something like that to have shipped to you, you can get it in less than a week. So it's a great service, and their boards have been flawless. So I can highly recommend them personally. I'm not affiliated with them, and I don't get any discounts from them. I just use them. I don't know how you give a discount for a board that costs $2. The particular board that we plan to have built will cost, because it's much larger than 100 by 100 millimeter, will probably end us costing us about $25, and that includes a solder mask stencil. So it's still really inexpensive, and that's for 10 boards. So it's a great deal. So that is our next step, finalizing the design of the board, getting the connectors correct for both types of relay boards, double checking it, making sure it looks like what we want, and then sending off and having that manufactured, and also buying the remainder of the relay boards that we will need to actually do this job. But before I quit, I still want to run another 10,000 or so cycles through this solid state relay board, although I'm very, very, very confident at this point that it will work, at least for these relays that are for these solenoids that we are driving right now. Now, there are more powerful solenoids in the pinball machine, like the flippers and stuff like that, that might still be a challenge for us down the road. So we'll have to check those things out when we get there. But for right now, it's looking very promising that this will probably handle what we need to handle. Thanks for watching. Have a great day.